All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Rafael Pastori, who is an assistant professor in Georgia Tech. He earned his PhD in applied mathematics and master's degree in statistics from Harvard University in 2020. Prior to Georgia Tech, he was a postdoctoral associate at MIT Mathematics, where he worked closely with the MIT IBM Watson AI lab. Rafael's research focuses on scientific machine learning at the intersection of applied mathematics and machine learning and inverse design via scientific machine learning and large-scale electromagnetic design. Today, Rafael will talk about input space scientific machine learning for PDE-constrained optimization of geometries, which sounds pretty interesting. So I'm sure we are going to hear a wonderful talk. Now let me ask a questions, Rafael, if it is okay, somewhat informal questions.
Sure.
To get to know you better and make this seminar somewhat informal. If you can share like how you got into this field and what motivated you and what makes you the most excited about the work you are doing right now, if you can share somewhat personal story, that would be awesome.
Yeah. Actually, I tackled that in my next slide. So if I can stop.
Oh, you do? Okay, yeah, just go ahead. Yes.
Yeah.
Please. Perfect.
So hi all, thank you, Young-Soo, for the invitation. I really appreciate it. The title is a mouthful, but I'm gonna speak about input space scientific machine learning for PDE-constrained optimization, and I will focus on geometries. And so I'm gonna explain a little more how I got into this by repeating parts of my resume, but also explaining like what happened during those lines. And so I started my PhD in 2014 in applied mathematics, and I was originally a physics student, so I came in as a physics student, and I was really interested in this optical devices called optical metasurfaces. So I did my training in France, where there was a lot of mathematics and physics, and I had just an interest in devices and design. And so when I joined as actually as a physics student and not an applied math student, and I was noticing that in the lab I joined for those optical metasurfaces, there was still a lot of heuristic-based optimization, and I was wondering that why are we not using the math? Like Maxwell's equation or linear equations should not be like impossible to leverage for like PDE-constrained optimization with a more like mathematical approach. And then I realized that like actually it was a difficult problem because there was a computational bottleneck. It was a difficult simulation problem before even being able to optimize it. And so I switched to applied math. Then I reapplied and switched to the applied math program, and focused on like creating a scalable approximate solver for optical metasurfaces. And then I continued doing that in my postdoc at MIT. But in fact, in my scalable approximate solver, one of the key components was to replace, it was basically a decomposition method that would break the design domain in many small subdomain simulation. And the key accelerating component was to train a data-driven model of the subdomain simulations. So it was fitting a good data-driven problem, and that's kind of how I got into surrogate models. So at first, my first surrogate models were I don't know if I talk about this today, but were polynomials. So they were not really, they were data driven, but they were not really machine learning. They were just traditional applied math. And then I was like, I hit the curse of dimensionality, and that's how I got into scientific machine learning and tried to do data efficiency. And that was the what I got. That was most of my research in scientific machine learning during my postdoc. And since then, so I started with solvers, then I was like, oh, I can accelerate with machine learning. And since then, since I started my faculty position, well, I continue trying to accelerate PDE solutions, but I also value the fact that we have great solvers for PDEs and that like they have the nice property, especially for Maxwell's equation, but also others, that like they certify the physics, right? We know that like the output is physical, and generalization is really something I've been struggling with in my scientific machine learning research. So I was like, oh, how can I leverage this scientific machine learning while still using PDE solvers that are certified? And so that's how I got into ML-enhanced PDE-constrained optimization that I'm going to talk about in the second part of my talk today. I also, in my group, have a research interest in end-to-end optimization and co-design. So where you're trying to optimize a physical device that needs to obey partial differential equations, but also end-to-end with software post-processing from the data you gather from that device. And also have an interest in more scientific machine learning problem, which is how to bridge theory-driven and data-driven models, and that's more for like model discovery and modeling in general for very complex systems. I'm going to talk about the ML-enhanced PDE-constrained optimization today. And one last point I wanted to make was that like I am doing a tenure track, and so it means that I will have a tenure case coming up in 2028. So if you receive an invitation to review my case, please send back something. You can say like, I don't like what Raphael does, but like send back something. That's very important for the tenure case. Anyways, so just to thank you for that question. I really appreciate it. Well, I want to frame a little bit like what I want to talk about today. The idea is like we want to discover a geometry. So geometry by geometry, I mean like the distribution of materials that will constitute a device later that you can fabricate through maybe additive manufacturing, 3D printing, or even lithography, depending on the application. And so you're in that situation where you have a parameterization of a geometry, this vector P, and you want to find the geometry, the vector P, that will maximize a function of physical fields. So we want to find a geometry that's optimized that PDE solution. Here, this F, I will limit it to scalar functions because we care about like maximizing one property. Of course, the physical fields are high dimensional. And so the impact of that kind of research is to produce a physical and fabricable design that would solve an engineering problem. And just like quickly for the people who think that like maybe like considering only scalar functions might be limiting, you can have like multiple goals that you need to take into account in your optimization. But by setting it as a scalar optimization, you can still do that. You just need to pick what is the goal you really want to maximize, and understand what are the goals that are more, constraints, like criteria that you need to meet, and those can be enforced as nonlinear constraints to your design. So here I kept like it's still a fairly general problem formulation. These are a few devices that I have worked with, or I am currently working with, to try to give a little more substance to those geometries that I'm talking about. So this is an example of optical metasurface. It's a really nice art rendering of a metasurface. It's basically using scattering properties of light to shape transmitted or reflected lights from those nanostructures. And they've been around for more than a decade now. And they're very compact in contrast to usual traditional optical devices, which rely more on propagative properties of light, and so they are usually thicker. I've worked also on thermal design here to imagine like that's basically a material you're trying to optimize its heat flux at some points, and what you can do is like punch holes at different places, and you want to know like where do you punch holes in order to get to your heat flux. So some thermal design. I am currently working on mechanical design and mechanical metamaterials, and fairly recently I also had a chemistry application where we were still optimizing an optical device, this metasurface again, but the goal here was chemistry, so it was a nice end-to-end optimization of optics and chemistry. Okay, and so my talk is about input space machine learning, and so I wanted to also define what I mean by input space. So I'm going to talk also. So the input space, by what I mean with input space, is that we're trying to do some representation or machine learning of the input to a PDE solver. So how to represent a geometry, and usually the geometry, then when you put in the PDE solver, it will impact the PDE solver in the coefficient of the PDE. And so we learn a representation of the input, and this is in contrast to output space machine learning, where we learn a representation of the solution. And so here the goal is more to accelerate PDE solver. So usually when we do output space machine learning, we're trying to replace that PDE solver. And the good thing with the output space machine learning, which is not what I'm going to do today, is that like it applies to many things. You can do PDE-constrained optimization, but you can also do decision-making, control, and uncertainty quantification using a similar model. So like you have like a lot of usability from it. It's had some success in the past with AlphaFold and things like that. But to me, there are a few drawbacks, and it's definitely not an obsolete field. It's a very thriving field. But I'm going to talk about input space machine learning today because of those drawbacks. Is that often we're trying to rediscover some known physics through data. So like if we already know the physics, why do we need to rediscover it? I already mentioned it. There's this lack of generalizability, and if we use a solver for optimization and it's not generalizable, and the design we end up having with this model is where the model is not physical, then we end up with a non-physical design, and that's not very useful. And that's also related, like those type of models, they're hard to certify or even to verify when you're using them to make sure that like they're giving you a meaningful result. So input space machine learning is what I'm going to talk about today. We're trying to learn a representation of the input of a PDE solver. And so this is more likely to work to have impact on PDE constraint design. At least that's the focus I've had. I haven't extended it to decision making, control, or UQ. And part of the reason is that we still have this idea of input space machine learning, is that like at least at optimization time, you still have a solver in the loop. We still have a PDE solver that you need to query. So the benefit is that you need to you have your physics that is certified because you delegated your physics to a solver that is transparent. And the question here is like, well, how can we leverage this machine learning? How can we create a representation, learn a representation that would shorten the lead time to discovery? And so in that context, the baseline really is it's going to be the state of the art in optimization rather than the state of the art in output space machine learning. So I'm going to talk about the state of the art optimization as a baseline today. I'm going to reduce the scope of my method to two cases. One, when you have a computational bottleneck, so solving for these fields is expensive, it hurts, so you don't want to do it like thousands of times, but you can still do it probably 1,000 times. So if you can just do it 3 times, I don't think the method I'm going to show, today is going to work. But if you can still do it like hundreds or 1,000 times, then that's the sweet spot of what I'm going to talk about today. The second scope is that, like, I'm talking about cases where F is nasty in the sense that, like, it's non-convex. It might have a landscape that has a lot of local optima. Why? It's because, like, I'm gonna compare myself against baselines that are gradient-based optimization, or the state of the art of optimization, and for convex functions. Or for well-behaved functions, then you might not need to improve the state of the art, and you might be already good with what already exists. So that's why I added that scope qualification, and then the last thing is that, like, the parametrization of the space, this geometry that you're trying to define, it's non-trivial to parameterize, and it could be represented, like, in a naive way with a very high dimensional feasible space, like thousands to millions to, I'm not going to show it today, but I have even a design that has 1 billion parameters. And so for that reason, the baseline I'm going to compare against really is gradient-based optimization, because other methods won't scale with this size of input. So what we want to compare against is gradient-based optimization, which scales, because even for PDEs, actually that's my next point, we have efficient ways to compute the gradients regardless of the number of parameters. And that's solving a related problem, which is the adjoint simulation. And for you all, I give just a refresher and maybe an insight on what the adjoint method is. This is actually the idea to understand is quite simple. So I like I teach those slides, but I think it's nice to go over it real quickly. So here, and I apologize, I changed the notation already, but here we try to optimize this P, that is the parameterization of the geometry. We try to find the parameterization P to maximize the objective function G of X and P. And so X are solutions to the PDE fields. And in what I told you before, really, P will affect G only through X. So it would be really like G in parentheses, G of X of P. But in what I've presented just before. And so, as I said, like, your X is a solution to a PDE. Here, just for simplicity, I present the reasoning for linear PDEs, and, like, where you already have discretized your PDE, and that's how you would solve a linear system. I show just after that you can relax that to nonlinear problems, so you can compute efficiently gradients to nonlinear problems as well. And so now you want to get the gradient of your objective with respect to your parameters. And so for this, you just have a chain rule. And in that chain rule, the problematic term is this one, G, the derivative of the partial derivative with respect to X times the partial derivative of X with respect to P. With a little bit of matrix calculus, we can find that like the derivative of the field with respect to one of the parameters pi would look like this. And so this term becomes this one here at the bottom. And if you look at it a little bit, if we parenthesize it that way, what it looks like is P solves. So we're solving, P is the dimension of the vector P. We need to do P simulations, A minus 1 times like, and we have this right-hand term. So that's not very efficient because if I have a billion parameters in P, now I need to do a billion simulations just to get the one single gradient. But the magic of the adjoint method is just that we reparenthesize this term here into the right-hand term, the right-hand side of this equation. And what we see now is that when we reparenthesize this, what we discover is that like, oh, we could do it as like solving a single simulation. Now it's not exactly the same simulation, and then we just need to multiply by a matrix. So that's where there's no magic in the adjoint method. It's just the chain rule and reparenthesizing. And so from this term, we derive the adjoint simulation, which is such. And that's where we see actually why it's called the adjoint simulation, because the adjoint simulation is basically the same linear simulation, but instead of taking the PDE operator, we take here it's transpose, but if it was complex, it would be its adjoint. And then we obtain that way, and once we compute our single adjoint simulation, we obtain that way very efficiently the gradient that we care about. So that's I'm not entirely sure why it's repeated, but that's the gist of it. And really, because the derivative operator is a linear operator, this extends to nonlinear PDEs. This will still, the adjoint simulation will still be a linear solve, and that comes really from the fact that the derivative operator is a linear operator. So, well, so gradient-based optimization is nice. It has this efficient computation of the gradient, so that's why it scales. And it's an efficient way to get to a local optimum. But, and so that's why, as I said, out of scope of this project are methods that are non-gradient based, because they would converge too slowly. At least that's the assumption I make here. And so what is wrong with the state of the art then? So there are a couple things that I think are problematic with this state of the art for PDE-constrained optimization of functions that are very non-convex. And the major problem I have with it is that it's essentially memoryless. What do I mean by that? I mean that when you have done an optimization run, so within optimization run, you might use information across iterations. Well, once you're done and you've arrived to a local optimum, and you're not happy with that local optimum, which happens often for very non-convex functions, then you need to start from scratch with another initial guess. And you cannot really use the information of all those PDE solves that you've done for your first optimization run. And as a reminder, each optimization steps, they can be costly because they require at least 2 PDE simulations, the forward simulation to evaluate the cost function and the adjoint simulation to evaluate the gradient. And so today's agenda is to look at input space machine learning for 2 goals. One is to accelerate the simulation via surrogate models, and the second is via enhancing exploration of the feasible space. So on accelerating simulation via surrogate models, it's usually what I would call output space machine learning, but I have and there is a lot of work in that space on physics-informed neural networks, which basically gives you a solver that is data-driven, not necessarily the fastest, but it has the benefit of solving an inverse problem as fast as the forward problem. So it can be useful sometimes in those settings. You have operator learning, and there are like end-to-end methods that can use this surrogate models of the output space. I'm going to focus on this physics-enhanced deep surrogate because even though there are some surrogate models that try to just accelerate the prediction of the function, it is somehow some input space machine learning. And so I wanted to start with that. So what is a surrogate model? Well, if I'm gonna use an illustrative example with optics here. So if I wanted to get the transmission through that structure, this is a 2D structure that is repeated at infinity left and right, and you have incoming light coming from the bottom, and you're trying to compute the complex transmission at the top. What you could do is just have that computational domain with periodic boundary conditions, solve Maxwell's equation, here Helmholtz equation, and then from the fields you computed, you get the transmission coefficient. The idea of a surrogate model, and here I want to clarify what I mean by surrogate model because it's not necessarily the same as in the literature. For me, a surrogate model is a data-driven of a scalar property of a solution to a PDE. So it's just trying to predict a property, here just the complex transmission, from a parameterization of the problem. Here the parameterization, it becomes the input of that surrogate model. Here the parameterization has like 10 geometrical parameters. It's the width of those squares, and one physical parameter, which is the frequency of the incoming light. And so the surrogate model, what does it do? It basically evaluates a data-driven model that will give you directly the complex transmission without having to go through the step of computing the PDE solution. And so because it skips that PDE solution part, it's much faster than using a solver. So it accelerates inverse design. Inverse design is another word for PDE-constrained optimization. And that doesn't tell the whole story because there's no free lunch. It's very fast at evaluation time, but you need to, in order for your data-driven model to be good, you need to train it. And so training requires to actually simulate the fields many times for many instances of geometries and frequency of input. And then you try to optimize the global error of your surrogate model in a data-driven way. Why the global error? Well, because it has to be accurate everywhere in the feasible space. Because if your optimization converges on a point where your surrogate model is non-physical, then your design is garbage, as I already mentioned. That's the problem of generalizability. And so a good goal for accuracy is to reach fabrication error or be dominated by it, because then it's no longer your model error that is dominating. There's no free lunch. If we reuse it enough times, then a surrogate model might be useful. But so I wanted I did an MBA before starting a PhD, which is pretty uncommon. Something that I liked and learned from my MBA is that we put very clearly cost comparisons, and so that's what I tried to make, because in scientific machine learning, less now, but at some point I thought it was useful to just be as clear as that. We want to have a method that costs less than the state of the art. So the state of the art would be to use a solver, call it R time. That's the number of iteration on our gradient-based optimization. And then we get to our design. The cost of the surrogate model is, of course, like we would need to call our surrogate model R time as well. But we need to add the cost of training that surrogate model. Otherwise, we introduced a method that is more expensive than the state of the art, and we want to reduce costs. And so just writing this very clearly, we can already motivate what are the research questions for data-driven surrogate model. We want to satisfy this inequality. So we want, here are our research questions. We want to be able to minimize training data, because here the cost of training is dominated by generating the data, which is solving the PDE many times and computing the property. And also we want to accelerate evaluation, so that like we really gain at evaluation time compared to solving the solution. As I said before, a good data-driven model doesn't necessarily require neural networks or machine learning in general. Chebyshev polynomials are actually very good for a smooth function. They're exponentially convergent, but they require the right choice of training points. And we'll see really briefly today that the choice of points matters also in machine learning. But here you can see, like, for about the same number of points using the same polynomials, if you use linearly spaced points instead of Chebyshev points, then Chebyshev polynomials do very poorly, right? You can see this stronger phenomenon where, like, it's really bad towards the end of the interval. And that is catastrophic for your global error, right? Because if you end up with a design that is in that region, your design is very non-physical. And it tells you, I like the example of polynomials because it tells us a lot. It also introduces the curse of dimensionality. The number of training data that we need for polynomials is a power of the number of the dimension of the input. And so that doesn't scale very well. And so the idea is like, okay, well, if we cannot do a Chebyshev interpolation and we still want more parameters, which we do because there's another key concept from optimization, which is the blessing of dimensionality, which means that when we have more degrees of freedom, we tend to do better. How can we get more degrees of freedom? And the idea is that, well, maybe neural networks can help because they tend to alleviate the curse of dimensionality without solving it completely, but alleviate it maybe better than polynomials. And so it's a problem of accuracy versus training cost. Now I'm putting pictures of André-Marie Ampère and James Clerk Maxwell. Why? And they don't look happy, as you can see. Why? Well, they worked really hard to find, for example, the equations of light, Maxwell's equation. And now we're talking about rediscovering their work through data. It seems a bit wasteful. And so the idea of the physics-enhanced deep surrogate that I'm going to introduce next is to put the PDE back inside the black box model. So physics-enhanced deep surrogate was published a couple of years ago in Nature Machine Intelligence. And so the idea is, like, we have a parametrization of the geometry. Here is just a cartoon of the geometry. Really, in the results is going to be this illustrative example I presented earlier with 10 parameters in the geometry. We have an accurate Maxwell solver. Thanks to it, we compute the transmission, and we're trying to reproduce that data, the link between geometry and complex transmission. The machine learning baseline that we use is to just have the same parameterization as input and trying to predict the complex transmission with a neural network. And so the idea of PEDS is to open the black box. The first thing we do with PEDS is to put a solver back inside the box. So the last layer of the model is a solver. But how is it, like, gaining us anything? Well, it's gaining us something because it's a low fidelity solver. So it evaluates much faster than the high accuracy solver. Unfortunately, it's also very wrong. So if we just use our low fidelity solver to compute the complex transmission, we would have terrible accuracy with errors like up to 100%, because in the case of Maxwell's equation, because those low fidelity solvers, in Maxwell's equation have resonances. It's resonance phenomena, and those low fidelity solvers, they usually get those resonances wrong. So if you get your resonance wrong very quickly, you have very large errors. So why am I presenting this in an input space machine learning presentation? It's because the method, the key of the method, is to leave the physics to the neural network, to leave the physics to the solver. And with the neural network, just trying to find what is the input that will make that solver accurate, not for the full solution, but just for the complex transmission, for that scalar property. And so that's the whole idea of PEDS. We have this end-to-end training of a neural network generator that will discover the geometry transformation from the original parametrization to what should be the input geometry to the solver to make it accurate for that property that we care about. So we were very happy with the results. In low data regime, that's just for Maxwell's equation, we could see 3 times improvement. Here, I just want to quickly mention that, like, here we used PEDS, and we also used an active learning algorithm that I didn't have time to introduce, but that just echoes the fact that, like, the choice of points matter. So we really want to compare those 2 methods, which are both using active learning, this creation of a data set that is most informative for the model we're training. We see that, like, in low data regime, like, we're 3 times better in accuracy. Now, this is still an accuracy that is too high for inverse design purpose, for PDE-constrained optimization purpose. But something we were also very excited about, this is too little data to say anything about asymptotics, but we could reach the fabrication error levels that we need to be dominated by fabrication error and no longer by model error. And so we could use that model for inverse design. We're very happy with that. And to show that, like, this is not just for Maxwell's equation, but for other types of PDE, this was illustrated on other PDEs as well, the diffusion equation and the reaction diffusion equation. An interesting thing is that the reaction diffusion equation is a nonlinear PDE, as you can see with this nonlinear term. And the low fidelity solver was not only a relaxation of the discretization, it was a coarse finite difference solver instead of a fine enough resolution, but it was also a relaxation of the physics. We did a linear relaxation of the physics here using just a diffusion equation instead of the reaction diffusion equation. For the diffusion and reaction diffusion equation, this is what the geometry looked like. We had Dirichlet boundary conditions and this structure in the geometry. And you can see that diffusion and reaction diffusion equation don't give the same solution for the same geometry. And so the results here is that we could decrease the evaluation costs. So by 500 times to 10,000 times. We could, so that's good. That was going back on my little, like, business-like equations. We reduced evaluation time. That was good. We also wanted to reduce the data cost and the data generation cost. And what we can show is that by multiplying the number of training data by 100, the neural network only baseline could still not reach the error reached by PEDS. So we have at least a reduction of 2 orders of magnitude in data cost needed. And so with such a method, we're much more likely to make a surrogate model worth it. Now I want to switch gear a little bit, though it's still input-based machine learning, and I want to talk about enhancing the exploration of the feasible space. So hopefully here, this is a familiar architecture now. I have a latent space. Here it was, before it was this parametrization of a geometry. Then I have a representation, and what should be familiar is that it should be familiar to PEDS. Here we had, like, the neural network generation of the input to a PDE solver. And here we have a PDE solver and then a property. The difference here is that now the PDE solver is not a low fidelity PDE solver. It is just a regular PDE solver that is, like, certifying the physics. And so we know that we can trust this outcome of the PDE property. But it comes at a cost. Now we need to solve the PDE every time we evaluate that pipeline. And so the goal is to get to a good optimum by reducing as much as possible the number of calls to the true solver. But what we gain is that we know for sure that the resulting design will be physical. And so this is all differentiable. You can evaluate with forward evaluation. You can backpropagate through this. Of course, you might need to determine your own primitive for the backpropagation rules on your PDE solver by introducing the adjoint simulation. That's going to be more efficient. And so we have that system. the question is like, well, how do we do input representation learning, right? We have that representation that we're now trying to learn. We're still doing ML enhancement of optimization. So we could try to have to get designs that are high performing, and then we try to learn a good representation of those designs, and that would probably learn the geometric features that makes a good design. Now that's a chicken and egg problem, because if I had already good designs for that property, I would probably not need to do any PDE constrained optimization. So we have that kind of problem, and the method I'm going to present next kind of solves that problem. But having that parameterization here gives us also many opportunities. It gives us control of the search space, of how we explore the feasible space. We can maybe like infuse some mathematical property to it. For example, we could reduce the dimension, so the input to this representation becomes a low-dimensional input instead of a high-dimensional input. We may leverage pre-trained representation and just do transfer learning and fine-tuning, and so we need less PDE solved to have a better parameterization. And another thing is that like the representation is independent from the solver that you use. So you might use like maybe a suite of solvers to get to learn your parameterization. At least a framework like that would be agnostic to it, so you could use whatever you prefer. I'm going to present in the next 6 minutes. Is that okay, Youngsoon? Youngsu? Is it okay if I have 6-7 minutes left?
It's okay.
Yeah. So this is work that was conducted by Reza Matzban in the group of Professor Ali Adibi, and together we developed this new method. And so the goal, just to show like what device we tried to do, we had this. There was this was published last year. There was this deflector that is useful in augmented reality, where you're trying to send light at a deflecting angle that is the same for red, green, and blue. And normally you have chromatic aberration and you don't deflect light at the same angle, but here we really wanted to have a design that would deflect light at the same angle for augmented reality applications. And the design that we have is this kind of a structure here that is repeated in X and Y direction with a given period, lambda X and lambda Y. And with different thicknesses, and of course a very complex pattern that is going to be repeated. And we try to optimize all those things to maximize the efficiency of the deflection in the angle that we care about. And so, as I said, the first problem we have is the chicken and egg problem. Like, how do we create a data set to learn a representation that would do just what we need? And for this, we used the state of the art of topology optimization. And a fact in topology optimization is that during a run in topology optimization, two things happen. These are heuristics, understanding of what happens. Often, first it tries to find a topology. Topology mathematically just means like where do you put holes in that geometry. And then it does shape optimization. So it changes the shape of those holes. So what we did to create our data set, we didn't do like full gradient-based optimization runs. We stopped them early using this early stopping. We stopped when we already had like a topology, but not the shape optimization was not done. So you can see here, for example, this is the evolution of our figure of merit. We're trying to maximize what's going on here. We can see that where we stop at step 35, we're not an optimum, right? Like it could probably do better it's not even a local optimum. It doesn't look like it. But we stop there because we already have some kind of topology that we can use. Now with that we just created 30 good designs. So we did 30 times 35 times 2 simulations to get the function evaluation and its gradient. And we augmented the dataset because 30 good designs was not enough, using also a heuristic from topology optimization, which is erosion and dilation. So here, for example, if you look at the white pattern, in a black background. If this is the design we came up with at iteration 35, we will also add this delayed version where we added a little bit of white everywhere, as if like, you know, it grew. And also this eroded version, as if like in the black area there was a lot of wind and it eroded this white structure. So we augmented through those heuristics our data set. Okay. And so so this is just explaining the same as what I just said. And then we trained our representation. The representation is reducing the design space from 6,000 degrees of freedom to 8 degrees of freedom. And in order to make that learning even more efficient, we used the vision transformer, which was pre-trained. So in the encoder, most of it was fixed. We just learned the last layer to get a meaningful latent space. And then we also had to train for the decoder. So we trained an autoencoder with most of the encoder was already transferred from a vision transformer. That was just trained on images, not really on like PDE-constrained designs. And then we could try to here we trained our latent space. We have those 8 parameters. Here I'm just showing like variations of the generated designs when we change just 1 parameters, and hopefully you can see that it really changes the structure as we change each of the parameters. It really captures geometric features, which we hope will help us get to good designs more quickly. And then now we, by reducing the feasible space from 6,000 dimension to just 8, and in fact we added even more like some physical parameters that are technically difficult to differentiate. They're not non-differentiable. It's just like from a software perspective, they're difficult to differentiate, such as the period of the structure and the thicknesses. Those are slightly harder to optimize. But we threw those parameters inside our Bayesian optimization. So we have trained our representation, and now we enabled Bayesian optimization directly on that latent space. And for this, at every step, we actually called the certified physics solver. We didn't try to learn the physics in a data-driven way. We just learned in a data-driven way a representation of the physics. Here, this is and so the run of Bayesian optimization took 350 iterations. Something that is interesting, this is color-coded with the figure of merit, the efficiency, which is this worst-case optimization for those for the deflection efficiency of those red, green, and blue colors. And we can see that at first it goes, and this is just to analyze. A posteriori, we did a PCA analysis, and we're just plotting those designs on the first and second components. And so we can see that at first it's exploring designs, and then like Bayesian optimization does, it started to exploit a little bit the designs and found one very good design. Here we also to compare, although we also had for comparison the paper from last year that was using topology optimization for the same problem. But in order to compare, we also did some topology optimization runs. Actually, is this? Oh, that's later. Okay, sorry. That is later. But with our Bayesian optimization, we arrived to very good results. 25% efficiency for red, 24% efficiency for green, 24% efficiency for blue. So it's more or less equal, and it performs really well the way we would want. For comparisons with topology optimization, we ran 70 runs of topology optimization, and we let it converge. More or less, on average, it was doing 200 iterations for each runs. And so it took about 14,000 simulations to do all those runs. And we can see that this problem is a non-convex problem. It's difficult. You get a lot of local optima that are not necessarily very good. It still got like some fairly good results, but the efficiency was not as good as like our approach, 25, 22, but 19% for blue. And so here again, like that's where like I want to show that, well, we really shortened the lead time to a design. We reduced the computational cost because here, in our case, we did 700 simulations to get our data set, and then 350 more or less to do the Bayesian optimization. So we're about at 1,000 simulations. And to do topology optimization, we needed to do 14,000 simulations. And in real life topology optimization, we kind of got lucky. We didn't do anything about fabrication constraints and ended up with Bayesian optimization with a fabricable design. But in topology optimization, often you end up with designs that are hard to fabricate. So you need to add this erosion and dilation optimization, where like you do the worst case of those three designs, the design, the eroded version, and the dilated version. And so that adds also cost, like three times the number of simulation. So really saying that like we reduce by an order of magnitude is kind of nice for TO. So we really shortened the path, and and we could also validate that structure. We fabricated it, and those very good design results that we got for our design translated into fairly good results also, definitely better than the former state of the art in experimental validation. We had a slight degradation for blue. I think if you look at the paper which we published on arXiv, we explained like why experimentally and with respect to fabrication this actually a posteriori was maybe expected. But in any case, we were very happy because this is a new state of the art. So hopefully I made a good case about ML-enhanced PDE-constrained optimization, and in particular, how focusing on this input space, focusing on engineering a search space, focusing on generating the geometry, these are three ways of saying the same thing, really can benefit, shorten the path to discovery of designs that would be mission critical and important, and all those designs would be certified by physics. I have applications in my research in mechanics, optics, chemistry, and thermics, like thermal property. Today I presented about optics. I'm definitely continuing to work in input space representation. I am also working on leveraging this for multi-physics application, and look more into transferring from pre-trained model and transforming also knowledge from multi-fidelity knowledge models. I also have those two other directions, and please don't hesitate to reach out if you're interested in any of those research directions. I have my email at the end of the presentation. I was not alone doing this. It takes a village to do great research. George Deck, I want to particularly thank Reza Mazban and Professor Ali Adibi, who were my close collaborator on that last work I showed you, and Reza really did the first-hand work, and also other collaborators. I hope I convinced you that input-space machine learning has good opportunities, and please don't hesitate to reach out.
Yeah, well, thank you. Thank you so much for the nice talk, Raphael. I'm sure many of us have enjoyed your talk. Let's have a Q&A sessions. Yeah, Kami, you raise your hand. Yeah, please.
Thank you, Young-Soo. Thank you, Raphael. Very interesting talk. I really enjoyed. I have a question about PEDS, Physics-Enhanced Deep Surrogate. In one of your slides, you mentioned that PEDS can kind of open the black box of machine learning. In the context of XAI, how do you think these PEDS can help us to provide physical interpretation for hyperparameters?
XAI?
Yes, explainable. How can we use it for
Explainable. Oh,
explainability?
yes. So that's the main. I mean, that was one of the motivation for having the output of the model be interpretable, transparent. We wanted the output to be computed from physical fields. We have this, although low fidelity solver, it still solves the governing equations, and so one of the motivation that I had for this type of architecture, and why, for example, I didn't do any correction after, like nonlinear correction that would add one more layer of neural network after that. The reason why I end with the physics is that now I can also look into what are the solution, what are the PDE fields that led to this prediction. And so I wanted to be able to, and I'm working on it, do some verification and like uncertainty quantification based on this physical layer. There is another physical layer, which is the geometry instead itself. So from that information of the geometry, which is interpretable, and the physics, which is also interpretable and understandable, we're really including a lot of explanation or explainability in the model. Does it answer your question?
Yes, thank you, Raphael.
Okay, thank you. Andrew, do you want to unmute and ask?
Yeah, hi, can you hear me?
Yes.
Yeah, thank you. Very nice talk. I really enjoyed it. I've thought about some of these topics myself. It was very nice how you laid it out. My question was about, in the last example that you were discussing, I think I heard you say something to the effect of, we're not learning a surrogate for the physics, we're learning a surrogate for a representation of the physics. Can you explain a little bit, or just clarify that point?
Yeah. So a very important point that, like, maybe I didn't make across very well is that we leave the physics to the solver. Like, the machine learning doesn't do anything with the physics. What it learns is a representation of the geometry, of the input to that solver. But the physics is done by the solver. We're no longer spending any simulation trying to learn something that is already known.
So the surrogate is from the, for instance, latent space parameterization to the output, and everything else in between is not learned.
So it's not to the output. So the output would be the property, right? So the representation, the output of our ML model is the input to the PDE solver. So the output is not containing any physics, it's just containing a geometry. And
Got it.
And that's a good thing, because geometry, I would say that's the non-reducible common space between all PDE-constrained optimizations runs, right? You're working, at least for geometry, you're working with the geometry. If you start looking directly at the solution, then it will be PDE dependent. It might be even PDE settings dependent. But the geometry itself is more likely to have transferable insights from even one PDE to the other.
Totally, I agree. Thank you.
Awesome. Jonas, do you want to unmute and ask a question?
Yes, of course. Raphael, thank you for that. That was really great. And I'm surprised that Lulu has not invited you yet to, or maybe he did invite you, but you weren't able to make it for a talk at Foundations Data Science. Because there's a lot of talks of this kind, and I'm like, this would be very relevant work because of the amount of people who do electromagnetics and like physics and applied physics departments over there at Yale. But anyways, so I wanted to ask about your use of the variable autoencoder for generating inverse design solutions. Yeah, I was curious because I know, I mean, variable autoencoder can mean a lot of things depending on the prior you set in the problem. I'm curious, because you have physical constraints, did you consider, or did you try to put those in the prior you're using here to help inform the solutions you're getting?
Do we though? Do we have physical constraints? Since we're just trying to create the geometry, we might have fabrication constraints. So that actually is that is a project I'm working on. Like, how do you infuse fabrication constraints in your representation? But we don't have physical constraints. In a way, we need to find geometry features that are useful for our physics later. So that's only in to that extent that we're trying to train end-to-end our model. But really the output is going to be that geometry. So just to clarify the point, we're working on the geometry. We're trying to find geometrical insights, and that's not going to be as much from learning the solution as to know like just what are the type of like shapes or latent features that like tend to work well.
Got it. Sorry, I guess I was using physical in a very general sense, not necessarily just physics-based, but literally physical, like what's physically possible as well.
So then now I'm going to start answering your question. So how do we learn a representation that is useful for our PDE problem, right? So to me, there are two methods to do that, to make sure we learn a representation that is relevant for our PDE optimization problem. The first one is the one I'm showing here. It would be an unsupervised learning approach. You don't have a data set, but you're just trying to optimize the property directly, right? So this, of course, is a way to learn a representation, and you can create a bottleneck or something. The problem is that now you have a learning process that has a PDE solver in the loop, and that's not even a low fidelity solver in the loop. So you want to really make it very efficient. And so that's why in that approach here, we had a data set approach, a supervised approach. And the way we infuse some information about what is a reasonably good design is to do this thing. It becomes more a question of how do I generate a good data set without it to cost too much, because we have this chicken and egg problem. And so here I would say one of the important contribution of that article, and if you want to see it, this is this archive article. It's currently under review. It's this data generation process. Here we actually use the state-of-the-art topology optimization to find topologies that were useful, because we thought, okay, topology will already have the geometrical content that we want to use. We don't really care about going all the way to a local optimum, because that's just going to tweak those features. But really, we just want to know the features. And then we're going to do our optimization on our representation to tweak the features afterwards.
I see. So in other words, this is almost like initial conditions for more refined optimization methods that already exist.
It's one way to say is this is a transfer learning approach. So instead of like here, we did 30 runs that we stopped early of topology optimization. Technically, all those runs in the prior state of the art of gradient-based optimization, none of those runs is useful because like they didn't end up with a useful geometry. And so with just gradient-based optimization, we just would have thrown all that away. And here, instead of that, we use that to create a data set and learn a representation. So that's the point I'm trying to make. Yeah.
I see. Okay, that makes a lot of sense, and I'm looking forward to seeing the archive paper. Then, thank you.
It's already on archive. Yeah.
Awesome. Okay, Sumanta, do you want to unmute yourself and ask questions?
Thank you so much for the presentation. I've been following your work for quite some time now, so it's finally a pleasure to actually see you give the talk. Thank you so much. So I have a couple of questions. The first one is kind of building on what Jonas just asked, which is on the VAE. So a lot of work which have used VAE for more like physics-based approaches, they don't really use the traditional way of matching the posterior with the univariate Gaussian, right? So the traditional way would be using a KL divergence to do that. But some people use other forms of loss function, for example, the MMD loss function and stuff like that. So what have you used, or what's your experience in that?
So here we didn't put any further regularization on what the latent space is. But of course, I think it would be very interesting to learn to structure that latent space to get further insight and make the representation transparent as well, understanding like, well, what actually drives the optimization. Does it answer a little bit your question?
Can you tell me what's your prior in this VAE?
Well, here really the optimization process we had is like, well, we used the vision transformer on ImageNet, and we fixed the parameters to it.
Okay.
And then we just optimized for just the simplest vanilla auto encoder. It's not even oh, is it variational? Yes, we probably did also. Yeah, you're right. Like we also had some. We forced a Gaussian in the latent space. I'm sorry.
Okay.
We did that. Yeah. Sorry.
Yeah. Because VAE comes from like using variational inference.
No, you're right. We did force a Gaussian in the.
Okay, thank you so much. And the second question is can you go back to the slide where you show the flow chart where you first have like you get the output of the neural network and then use the FD solver on that? Yeah, this. So this is very interesting because as you just said, you use the neural network to have an output and then you use the PDE solver on that output, right? And the neural network is trying to achieve something. As you said, it's a interpretable representation of the geometry, right? So now, I've seen a lot of people who have similar approaches where they use the PDE solver instead of using an autodiff and stuff like that in order to enforce the physics, right? But when we do that, the traditional laws that apply to numerical methods, for example, if we are using a finite difference solver to solve an advection equation, then probably it's not like the rules of the stability and everything comes into play, right? So for example, we should not use a forward stepping the forward time stepper for the advection term, and we should not use this for that, etc., etc. But when we use that as a surrogate for the autodiff, those rules just go away. So we can just blindly use a central difference method for even time and space and stuff like that, because right now we are not really using the finite difference in the traditional numerical linear algebra kind of a way, but it's much more in optimization way. Did you find something of similar nature when you're trying to use that over here? I mean, am I able to?
No, we didn't. I mean, it was, it's a solver to Maxwell's equation, and we didn't have. Well, okay. The only moment where this might have happened is during our Bayesian optimization, right? Because during it could have happened also during the topology optimization, but we didn't have the optimization run lead us to an input that the solver doesn't converge on. And then in the Bayesian optimization setting, we also did not, although it doesn't matter as much because you basically, it's more of a sampling based method. So if one doesn't work, like you can still sample others. But yeah, so does it answer your question that so I would say to apply that to a system where, there are a lot of geometries where like your solver doesn't converge, so it's basically you have I would say it's in between the software issue and the physical issue. Then you need to think about, as I said, the good thing about this representation learning is that it's agnostic to the solver. So maybe you can learn, you can do a progression of solvers, maybe start the optimization with like a solver that maybe is not as accurate, but that will converge every time. And then as you fine tune, maybe go towards a solver where it's gonna be closer to your problem, but you will have also in your batch a few cases that are not gonna run. So you need to handle your errors.
Oh, so if I ask this question, can I use a second order RK method to solve a fourth order equation using this?
So again, this is independent of the solver. So you can use the solver that solves whatever you want.
Okay. Yeah. That's what I'm asking.
Okay. Well, thank you. Next question is by Jan van Delden. If you are there, do you want to unmute yourself and ask the question yourself? Or do you want me to read your question because that's on the chat box? I can read the questions. Okay, thanks for the great talk. In your latent space optimization example, how much did the size of the latent space impact the optimization result? Or how much did the number and quality of topology optimization samples impact the quality, the performance?
That's a very good question. This article is not first step. It opens a lot of questions. Something we like about that article, that I like in particular, is that like the proof is in the pudding too, right? Like using this method, even though there are still open questions on, for example, like how do you use the number of latent parameters or and things like that, we still got the new state of the art. So that was a very impactful validation. But that is a good question. I think you got I delivered the message well, because those questions are very relevant. And in my opinion, I don't have a better answer than the current literature on autoencoders and choice of variables and things like that, and latent variables and all.
Okay, sounds good. Next question is by Mohammed. He's asking, there is a Julia package called infinite-opt.julia that lets you model design problems where the control variables is a full space or time-dependent field. Could your latent space plus Bayesian optimization workflow serve as a practical low-dimensional surrogate for that kind of infinite-dimensional control, still allowing PDE and reliability constraints?
I would say no, because again, here the machine learning is not learning a surrogate for the physics, right? It's learning a surrogate for the geometry or the input. But I do think right now I presented within the scope of PDE-constrained optimization of geometry. I do think there might be a way of applying that to control. So if you have a geometry that evolves in time, that's already a control problem. I do think there are ways to leverage this type of thinking, leaving the physics to the solver, but still using machine learning to engineer the search space. I think there are probably ways to do it, but I haven't done it yet.
Okay. Well, there's no more questions from the chat, but I get to ask at least one questions. Finally. Well, I guess it's not a question. It's more like a comment and suggestions to add one more item in your future directions. I mean, it's nice that you have introduced a way of tackling the input space in the context of the PDE-constrained design optimizations in various ways. But maybe you want to look into how to bring the scientific ML in PDE solver itself. And if you're just looking into traditional numerical method of solving PDE, the input of that could be, one of the input could be, that basis representation, like the polynomial basis representation, which you have mentioned in your introductory slide.
Yeah.
Maybe we can change that, replace that to the data-driven basis in order to improve the quality. That's another way of bringing this scientific ML into the numerical solver itself. Recently, we have published a preprint talking about the foundation models in computational science, and also introduced the framework, so-called the DDFM, data-driven finite method. I can share that with you, and that exactly talks about, that kind of input. It's different from your input space.
Yeah.
But perhaps you want to look into that. Yeah.
Yes, and I'm familiar with that work because I read the preprint. I think
you read it? Okay.
Yes,
cool.
I do think there is you sent it to me, but it was a while back. I think there is definitely a great opportunity here. I learn a representation of the input of the physical object, the device, right? Because that's but and I'm assuming that, like, the solver will do its job. But maybe sometimes that, we talked about that in Q&A, and I think it's an important problem. Sometimes, you also need to make good decisions of hyperparameters in the solver to make sure the simulation doesn't iterate forever, or to make sure the simulation even just converges. And so There are two ways. Either you could just learn a representation to learn this, not just physics parameter, but also numerical parameters, that hyperparameters that you need. That's one way. Or you can try to also infer these parameters from the low-dimensional representation that you create of the geometry. The rationale here would be to say, well, if those geometries are similar in a sense of they are similar in a similar position in the latent space, then probably the solver will need similar hyperparameters to solve this geometry efficiently. So I think there are two ways to leverage. Either you use the method directly on numerical parameters, or you leverage the learned representation of the geometry, because in the end, those implementation of the solver will really be dependent on the geometry, on the mesh and things like that. And so they're probably this latent space, in particular, if it's a compressed latent space with low dimensionality, might help also to infer. So there is definitely synergies to do there. Yeah, I agree.
All right, sounds good. Well, let's end here because we already passed like 20 minutes past the the promised time, ending time.
Yes.
Well, thank you so much for the nice talk. Let's thank our speaker Raphael for the nice talk, and as well as a wonderful Q&A sessions. Thank you so much,
Thank you.
Raphael. So with that, yeah, go ahead.
Yeah, hopefully, if you're interested, like send me an email. I will be happy to answer. I'm open for collaborations.
Of course, it looks like the Sumanta has a couple of more questions, so he will email you for sure.
Fantastic. Yeah.
Okay, so with that, let's end our seminar today, and let me push the stop button for the recording.